Hello friends, in this video I'd like to solve the following problem from Lowell Putnam Mathematical Competition year 2010, problem A2. We wish to find all differentiable functions f from the set of real numbers into itself, satisfying the following equality. F prime of x equals f of x plus n minus f of x all over n for all real numbers x and positive integers n. So here are my hints for this functional equation. First, justify that our function is not only once differentiable, but actually twice differentiable. In fact, it is infinitely many times differentiable. That should be pretty easy, because notice that from this equality, for example for n equals 1, notice that the right-hand side is differentiable, so the left-hand side is also differentiable. And then, make the following three settings of variables. First, set xn to be t1, then set it to be t plus 1, 1, and finally set it to be t2, to show that f of t plus 1 equals f prime of t for all real numbers t. And from there, you should be able to justify that the second derivative of our function is constantly 0. And recall this fact about polynomials, that if p is differentiable k times, any function whatsoever, if it is differentiable k times and its kth derivative is constantly 0, then this function is a polynomial of degree at most k minus 1. At most k minus 1. So if k double prime is 0, that means that our function is of degree at most 1. So give this problem a try, and I will see you in just a minute. Alright, so maybe let's call our functional equation asterisk, and I will set the following. First, I will set x and n to be t1, then I will set x and n to be t plus 1, 1, and finally I will set x and n to be t2. Notice that we can derive the following formula. F prime of t equals, well, f of t plus 1 minus f of t. Very well. From the second setting of variables, f prime of t plus 1 equals f of t plus 2 minus f of t plus 1. Alright, and from the last setting, after multiplication by 2, we can derive 2 times f prime of t equals f of t plus 2 minus f of t. Minus f of t. Right. And now, and you know what, I will do the following to be clearer. I will put minus here, and plus here. I have just changed signs. Let's take these three equations and let's just add them together. Let's add them together and we'll have the following. F prime of t plus 1 minus f prime of t, and notice that on the right hand side this cancels with that, this with that, and this with that, so we are left with 0 on the right hand side. So we have derived this formula. For every real number t, f prime of t plus 1 equals f prime of t. So our derivative is periodic, of period 1. Fantastic. And now what I will do, I will take my functional equation once again, and I will set x to be, I will set n to be 1. Yes, I will, of course. So let's set x and n once again to be t1. Then once again, let's write this equation. We have f prime of t equals f of t plus 1 minus f of t. Alright, but now let's notice that the right hand side is really differentiable. this part right here is differentiable. Because here we have function f, it's differentiable. Here we have function f composed with a linear function, so it's also differentiable. The difference of two differentiable functions is again differentiable. So let's take this equation, this equality, and let's differentiate it on both sides. So we have f double prime of t equals f prime of t plus 1 minus f prime of t. Alright, but now we will use this condition, which I will mark triangle. Notice that f prime of t plus 1 minus f prime of t, it's 0 by condition triangle. So our function f is twice differentiable and its second derivative is constantly 0, which means that f must be a polynomial of degree of at most 1, i.e. it must be a linear function, i.e. affine function, sorry, not linear, but affine function. Let's keep terminology straight. So it's f of x equals ax plus b for some constants a and b. Now, what we have to do in the end is to do the verification. And we will be left home. Verification. All right. On the right hand side, so let x be a real number, let n be a positive integer. Then on the right hand side, let's start with the right hand side. Right hand side, it's f of x plus n minus f of x over n. So now we have what? A x plus n plus b minus ax plus b all over n, and we are left with what? In the numerator we have an, and here we have n, so it's a. And notice that what is a? It's the same as the derivative of our function, which is on the left hand side. Which means that our function has our equation has infinitely many solutions. So solutions, well, f of x equals ax plus b for all real numbers x, where a and b are any real numbers. And that closes our problem. So any affine function solves our equation. So thank you very much for watching. I hope that you've learned something new. And by the way, one more thing. Our assumptions were, well, much generous because it was assumed to be true for any positive integer n, and in fact, all we needed is n equals 1 and 2. So our condition can be weakened to just assume that n is either 1 or 2. But it was stated in a more general form. So that is it. So thank you very much for watching. I hope that you've learned something new this time, and I will see you next time. Goodbye.